Welcome everyone. My name is Lasse, and in today's lecture we're going to discuss numerical methods for model predictive control. And so this lecture assumes that you already have a good understanding of the high-level idea of model predictive control, or MPC for short. And in today's lecture we're going to look into some of the mathematical tools that are used in the background to solve these problems. And so let's begin by briefly reviewing the high-level idea of MPC. So let's look at this example of a car following a racetrack, the circular racetrack, which is given by this dashed reference. And the idea of MPC is that at every time step, we look at our current state, which in this case may, for example, be the position and heading of this car and its velocity. And then we make a plan for a fixed or a finite time into the future. So maybe 20 or 30 time steps into the future, using a model to make these predictions and optimizing our plan, our receding horizon plan. So the plan that is stretching in a fixed distance into the future for a given objective. And so the high-level idea is as follows. We always take the current state, and then we have some objective, for example, minimize the deviation from this reference while also maximizing progress along the track. And then this state and the objective are handed over to this MPC module that is making predictions into the future and optimizes the controls, so the inputs to the system, for example, the steering and brake pedal commands, to minimize the cost, so to fulfill this objective. And then we have a plan for, say, a couple of time steps into the future, maybe 20 or 50, but we will only apply the very first of those inputs. And then from there we start again. So we again take the state, we plug it into our MPC module to update, to get a new receding horizon plan, so a new plan into the future. We again take only the first step, so we again only apply the first input, and so we do this in a loop. And in this framework, there's one important part which we will focus on today, which is the optimizer. So the tool that is the tool that is optimizing this trajectory to fulfill our objective, so to minimize the cost J. And so the mathematical formulation of this optimization in the inner loop was as follows. So we could cast this control problem as constraint optimization, where our task was to minimize some cost function J by choosing suitable states X and inputs U, and this is a sequence of states and inputs U over the prediction horizon into the future, where the prediction horizon is capital T. But we are not interested in arbitrary states or inputs, or we can't just choose them arbitrarily, but they are coupled because they need to be dynamically feasible. That is, the states that we are choosing, they must be achievable by the dynamics model that we have. And so, for example, if we have a car, we can steer and we can accelerate to the front and back, but we cannot immediately move sideways because the tires are preventing us from doing that. And so we have dynamic feasibility as an equality constraint here. And then we may additionally have some state and input constraints, meaning that we can only choose certain controls. Maybe we have a maximum acceleration, or for the state, a maximum velocity that we allow, or a maximum deviation from the track. And finally, we have an initial constraint, initial state constraint, meaning that all our plans must start from this X init, which we may get from our state estimation pipeline. So we know where we are now, and the objective is telling us what we want to do, so make progress along the track. And we have to make sure that all our states start from our current position. And just as a quick reminder on notation, we use this X1 to capital T and U1 to capital T to denote the tuple of all of these states and inputs. Okay, and so at at our previous lecture where we've discussed the high-level idea of MPC, which you can also find on this channel, there we've just assumed that we have access to some software tool to solve this problem. So that lecture is focused on how can we synthesize a given, so how can we write a given control problem as an optimization problem. And then once we have that, we have this formulation that we can hand over to one of these libraries, for example, Casadi, which is a numerical optimization library or constraint optimization library, which has interfaces for C++, Python, and MATLAB. Or there's also Jump, which is a similar library in Julia. And all of these libraries work in a way that you have your problem description. So here's a very simplified toy problem of constraint optimization. And you can make a symbolic description in a very compact form of this problem, and then just hand it over to the optimizer and it will solve it for you. Now, in today's lecture, we want to sort of get rid of this assumption that we just have some tool that it magically tells us the solution. Instead, we want to look behind the curtains of what is involved in order to solve these kinds of problems. And so, yeah, so that's the focus of today. We'll look at the numerical background of these tools. And before we dive into these methods, I want to quickly simplify the problem a little bit for the scope of this lecture. And so here we have a slightly reduced problem formulation where we don't have state and input constraints. So we will drop these constraints where the controls can only be in a specific set and the states can only be in a specific set. So the only constraints we are left with are the constraints for initial conditions and for dynamic feasibility. And so yeah, we end up with this smaller problem, which is to some extent simpler to solve. Okay, and so another thing I want to remind you is that, and that's also something we've already introduced in the previous lecture, is that we will assume that our objective is time separable. That is, we don't just have an arbitrary cost function here, but we assume that we can write this cost as a sum of stage costs, meaning that there are these small g, so g of x and t, so of the state and input at each time step, and we can write the total cost as the sum of these stage costs. So the total cost over the entire horizon will be the cost at the first, at the second, plus the third, and so on. And so this will be an important assumption for some of the tools that we will develop throughout this lecture. Okay, and so before we directly dive into how we can solve the problem, I want to introduce one very important tool that we will make use of throughout this lecture, which is the idea of state elimination. And the idea of that is that we can reduce the problem even further by getting rid of the state decision variables and converting this problem that you've seen on the previous slide into an unconstrained optimization problem. And so I'm hoping that you may recognize that as something that you've already seen in other disciplines, so to make that more familiar to you. And so the idea of state elimination builds on this idea of forward simulation, which is that we have this very specific structure of the problem, that all the states are always connected to the previous state via the dynamics constraints. And so if we have the initial conditions, which we will be given by our state estimation pipeline, for example, and then we can get rid of all the future states by writing them in terms of controls. So the idea is that in the end, we only want to have the control variables, so the u1 to t, as decision variables in our optimization, and we don't want to have the states. And so the idea is that we can write, trivially, we can write x1 as x init, because that's just our initial constraint. And then x2 we can write as just simulating the dynamics one step forward in time. So we apply f, which was our dynamics function, which takes x one step into the future. And so we can apply f on the initial state with the first input, and we get the second state. And we can do that recursively, so we can do it again for x3. We just apply 2 times f, where the inner f takes the initial state and applies the first input, and then the outer dynamics take that resulting state, which is now x2, and applies u2. And so we can do this one after another, and so we can define this function ft, where ft is the function that takes the initial state at time step t, and then the sequence of controls ranging from that small t, so the intermediate time step small t to capital T, so until the end of the horizon, and it will give us the resulting trajectory, so the induced trajectory that we just get from applying these inputs in open loop from that state. And so f1 is, for example, this forward simulation function starting from the initial state, so from x1, and that's just the thing that we've seen on the previous slide. And so that exactly gives us the entire trajectory if we plug in the initial state and the entire sequence of controls. Now, why is this useful? So we can use this to eliminate the state variables and rewrite our objectives in terms of only controls and initial conditions. So if we use this forward simulation function starting at the first time step, then we can write our original objective, which depended upon states and inputs, now as this new objective j tilde, which only depends on the controls u1 to t, so the control sequence and the initial state. And we can do that by substituting the first. So here originally we had to plug in this sequence of states, but now instead we plug in the forward simulated sequence. So this forward simulation function f1 will give us x1 to t, and so that's exactly what we needed as the first argument to our original cost function. And so with this rewritten objective, the nice thing is that now we have an unconstrained optimization problem, which with fewer decision variables. So now we only depend upon these inputs u1 to ut, and the initial conditions, they are given, so they are not a decision variable, they are just fixed. And the nice thing is that not only do we have fewer decision variables, but we don't have any constraints, because all the constraints, so the initial conditions and the dynamics constraints, they're implicitly satisfied, because the forward simulation function will always produce dynamically feasible states. And so with this rewriting of the problem, we have just an unconstrained optimization problem that may have already seen in other disciplines. And so you essentially get some cost landscape. Here we just plotted it for 2 decision variables. So say you had only u1 and u2, and these were only scalars. Then maybe the cost looks something like this. And your task is now to minimize this cost by taking a suitable choice of these control inputs. And in general, this cannot be done analytically, so we can't just say, okay, this is the minimum, we can just step there. Instead, we have to take an iterative approach to approximating this. And I'm sure you've maybe already seen this in another context, where you may take gradient descent, so small steps in the steepest direction of descent, so in the opposite gradient direction, towards a local minimum, or maybe even a Newton's method. And we'll get to these kinds of methods later throughout the talk. But before we do that, I want to we will do a bit of a deep dive into a special case, which is these unconstrained problems, or problems with convex quadratic costs, meaning that the cost has only up to squared terms of the decision variable, so it's a polynomial where the highest term is a squared term. And so we get these sort of, in multi-dimensions, we get these quadratic surfaces, or in 1 dimension you would just get a parabola. And so for these convex quadratic costs, the nice thing is that we can compute the minimum analytically. So here we could just say, if we had this entire cost landscape, we could just directly step to this global minimum by taking the gradient of this quadratic function and just setting it to 0. And so we're just solving for the point where the gradient of this function is 0. And this kind of special case also exists in optimal control, so which is called the linear quadratic regulator. And so the linear quadratic regulator is a special case of an optimal control problem where the dynamics are linear and the costs are quadratic. And so this is exactly the OCP that we've seen earlier, just with these additional assumptions. So we want to minimize over states and inputs to minimize this objective, where this objective now takes a very special form. So it's the sum of these squared terms, where the deviation from x from the origin is penalized with some cost matrix Q, and the deviation of the input, so any non-zero input, is penalized with the cost matrix R. And our total cost is just the sum of these stage costs over time. And then our dynamics, so these are the quadratic costs, and then the dynamics, which are linear, are take this form, where the state at the next time step is always a times x at the previous time plus b times u. So this is just a linear equation of how the state evolves over time. And of course we still have our initial conditions. And the last important assumption that we will make use of here is that Q must be symmetric, so Q must equal its transpose, and must also be positive semi-definite, which means that it must have eigenvalues greater or equal to 0, and R must be strictly positive definite, meaning that it must have eigenvalues only greater than 0. With that problem description at hand, we can attempt to solve the LQR problem, and the first approach that I want to show here is the so-called batch solution. And so the batch solution attempts to solve for all controls at once, so in one batch for the entire horizon. And it does so by exactly exploiting this idea of state elimination that we've seen earlier, and this will allow us to cast the LQR problem essentially as a linear least squares problem. And so let's look at what the forward simulation idea looks like for the linear dynamics. And so this is exactly what we've seen earlier. For x1, we just get the initial state, and then for the later states, we can exploit this very special structure of the linear dynamics. So for x2, it's just a times the initial state plus b times u1. And then for all the later states, we just always take the previous expression, which is the previous state. We multiply it from the left with this A matrix, and then we add b times the input at that time. And so because of this very special structure of the dynamics, we can write it down in this compact expression for an arbitrary time step into the future, all the way up to capital T. And now we'll, using this forward simulation idea, we can also write the forward simulation function as a single matrix equation. So here we just stacked all of the states into one long vector, so that we call this now capital X. And then we can, so this is the trajectory that we want to find. And we can find this trajectory with this matrix equation simply by multiplying the initial state with this stacked matrix, which we call A over bar, and then we collect all the terms that were multiplied with U into a capital, so B over bar matrix, and we also have the stacked inputs here. And so you can convince yourself that this matrix expression is exactly doing the same thing as we've seen on the previous slide. So for example, x1 is just the identity matrix times x in it, and then there's no, these entries are all 0, so no input is applied, and then x2 is just A times the initial state plus B times U1, and all the other entries are 0. So all the other U's get multiplied with zeros here. And with this matrix equation at hand, we can just write the entire forward simulation as this compact matrix expression. And for this sort of matrix form of our problem, where we've now stacked all our states and inputs into long vectors, we can also define new cost matrices. And so we will form this block diagonal Q over bar, which just consists of the Q's at every time step stacked along the diagonal as block matrices. And then R over bar just stacks takes the block diagonal of the original control cost matrices R. And with this at hand, we can write a new cost J over bar, which can now be compactly expressed only in terms of these stacked states and inputs, simply by multiplying this Q from left and right with X and R from left and right with U. And so this looks very similar like our original stage cost, so the cost at a single time step, but now this expresses the cost for the entire horizon, because these are also the stacked states for the entire horizon and the stacked controls for the entire horizon. And so this will this will represent the exact same objective, so encode the same task as we originally had. And combining this rewritten cost with the idea of forward simulation that we've seen earlier, we can now write again our tilde cost. We take our objective and then this objective in terms of the stacked states, and then we also had this forward simulation function as a matrix expression. And so we can replace each of the axes in this expression with the corresponding forward simulation. And if we rearrange the terms and sort of tidy up this expression a little bit, then we get this compact J tilde, right? So that's the cost in terms of only the sequence of all the inputs with state constraints eliminated. And we can write it as this quadratic expression in U. So U is just left and right multiplied onto this H matrix, and then there's also some linear term and a constant in U. And so this H matrix is, for example, what you see down here. So it has exactly the same shape as our original block diagonalized control matrix. So, right. And with this reduced cost, which now only depends on the inputs, but on the sequence of all the inputs, we can write the batch formulation of LQR as a linear least squares problem. And so this is the unconstrained optimization problem that represents the LQR's problem as a single batch. So we need to solve over all the inputs U in one go for our J tilde. And if we look at this is a quadratic expression in U. So this is a polynomial just where U are vectors, and the highest term that is showing up is a squared term. And so we can check that H is so this is convex because H is positive definite by construction, because R we assume to be positive definite and Q we assume to be positive semi-definite. And so you can show that this will always be convex, meaning that it's sort of upwards curved, the cost landscape. And so that allows us to solve for the minimum, the global minimum of this expression, simply by setting the gradient to 0. And so we can take the gradient here of exactly this expression, set it to 0, and then solve for the input. And so that will involve sort of bringing U star, which is the optimal controls that we are looking for, to the side. And so we need to take here the inverse of H in order to do so. Okay, that concludes the section on the batch approach to LQR. And so to summarize, this approach exploited the fact that we can eliminate the state variables with linear dynamics in a very specific way to write this problem as an unconstrained optimization problem, which we can recognize to be a linear least squares problem. And then this problem allows us, or this formulation allows us to directly solve for all controls in one batch. A few comments on this approach. So the nice thing about that approach is that we can solve it analytically, which is derived from the fact that it is a convex quadratic problem. And so this is much more efficient than having to take small steps towards a local solution. Instead, we can find the global solution simply by solving a linear system of equations. But still, this requires us to invert this rather large matrix, which has the dimensions mt, where m is the number of controls that we have and t is the number of time steps that we have in our planning horizon, times mt. So it was this big matrix H. And so this dependence on the time horizon here makes it a bit problematic, because if we have a lot of time steps into the future, then computing this inverse may be quite expensive. And so the question is, can we do better? And the short answer is yes. And so the idea that we can follow is this idea of dynamic programming, which gives rise to a different solution to LQR. So technically, dynamic programming can also be applied to different settings, but in this LQR setting, it works out quite nicely. And so the main idea that we will exploit is that we can exploit the sequential structure of the problem induced by the dynamics even more to compute not only the forward simulation, but also to compute a more efficient inverse of this H matrix. And so before we dive into the math, I want to quickly highlight the underlying principle that allows us to perform this dynamic programming idea. And this is the principle of optimality. And here we'll just start with an example before we come up with a formal definition. And so imagine that you are tasked to find a plan to this goal location C, and you're starting in A. And so you know this optimal plan from A to C. Imagine that you already know this plan, and this optimal plan leads through B. Now, the principle of optimality states that if this is the optimal plan from A to C, then you can also take any tail portion of the plan, for example, this tail bit that starts in B and ends in C, and this will still be the optimal plan for this tail problem. Meaning that if we are in B and we're asking ourselves what is the best way to get to C, we can just sort of truncate or get this tail portion of our original plan and invoke that. And it should be easy to convince yourself that this is true. Imagine we can just sort of try to find a counter example or contradict it. Imagine there was a alternative plan from B to C that was better. So imagine that this has a lower cost from B to C. Then obviously from B to C would take this gray route. But if that was true, then our original plan would also take this gray route from B to C. So it cannot have been optimal in the first place. And so the summary is that we can always take any tail portion of the plan and it will be still optimal for the tail problem. More formally, imagine that you know the optimal solution to some optimal control problem. So we know the optimal sequence of states, of inputs. You start from 1 to capital T, where T is the planning horizon, and then following these controls will induce this state trajectory, X star. Then any tail sequence of this original control sequence, starting at some intermediate time step, small t, so from small t to capital T, will also be the optimal solution to this tail problem over this cost to go jt, where the cost to go jt is just the stage cost summed up starting from small t to capital T. So this cost just cares about all the stage costs after our intermediate time step t. And so this tail problem says we want to minimize this cost to go starting from t into the future with only the tail constraints and with the initial condition that we start on our optimal trajectory at time t. And so this is exactly the same as the example that we've seen on the previous slide. And so dynamic programming exploits this idea of, or this principle of optimality in a very specific way. And it uses it to break up the problem into smaller problems that may be, so smaller tail problems that may be simple to solve. And so imagine again the same setting that we are trying to find a plan, a way to go to C. And now we don't know where we start from. So previously we knew, okay, we start from A. Now we just say, okay, we want to go to C from an arbitrary state in this setting. And so we start from C, and then we go to some intermediate time step here T, and we enumerate all the states that we could possibly be at that time. So for example, we could be at this state, and then we solve the optimal control problem from this state into the future to reach C. And then we also do that for this intermediate, for this state here, which was our original intermediate state B. And we get this tail plan, and we can do it for the bottom one. And so we have to do it for all the states. And so the controls that we compute, they are not a fixed sequence of controls, but rather they are a function of this state that I will be at. And I have to compute this, these controls. So we have to compute this entire function, meaning we have to find the controls for all possible states. And in addition to that, we will also record the optimal cost to go, which is the cost that we incur if we follow the optimal plan, meaning that what is the cost that we have to pay even if we played optimally from here onwards into the future. So for this state up here, even though we found the best possible sequence of controls, we still have a cost of 10 in this example. And here we have a cost of 1, and here a cost of 4. And so we denote this optimal cost to go by J star. And again, J star T is a function of the state because what the cost that we will incur in the future depends on where we are at this time step. And using this optimal cost to go, we can now extend the tail problem into backward in time. And so here we've just divided the whole horizon into 2 steps. So we have this intermediate time step and then the initial time, but technically you could also take many small steps. And so here we now have to look again, okay, at which states, at which of these states, we have to enumerate all of the states, and then we have to again solve an optimal control problem. But here we don't minimize greedily how can we reach any of these states. So we don't just care about the immediate cost, but we minimize the immediate cost until time t plus the cost to go that we would incur from there on to the future. So for example, if we were in this state, then this would be the optimal trajectory because this has a potentially, maybe it has a high cost, but then at least here when we reach the state B, we have a small cost to go. And so because, for example, this top state here has a very high cost to go, none of these states decided to go there because even though maybe we can reach this state quite cheaply, whatever we can do there will be quite expensive. And so even the optimal cost to go is still quite high. And so now we have the second sort of portion of the plan, which is again a function of the state now, a function of the initial state. And once we have this function, which is a feedback strategy because it maps a state to controls, we can now plug in our initial conditions. And so we say, okay, we were at state A, and if we are at state A, we can just evaluate this. We can just evaluate the feedback strategy at that state, and we recover our original plan. Okay, and so just a few comments on this idea of dynamic programming. So you may think this is a, from this example, you may think this is a horrible idea because you have to now, instead of being able to solve just a single, sort of for a single initial conditions initial condition to a specific goal, we now have to solve for all possible states that we could be at. And in general, that poses a challenge, because that means that we need to be able to represent this optimal cost to go, J star T, as a function of state, for example. And so this optimal cost to go is defined as the original cost to go evaluated at the optimal strategy and the corresponding states that we get from forward simulating these this strategy. And so a naive approach to represent this optimal cost to go would, for example, be to discretize the state into small volumes and then compute this cost to go, so solve the optimal control problem for each of these small volumes, for each of these possible regions of the state space that we could be in, and then just compute this lookup table. And then when we sort of want to evaluate this function, we just look up the value in this discretized setting. And so while that is in general possible, it is often a bad idea, because this approach requires you to solve an exponential number of problems in the state dimension, and you also have to make a choice about the discretization. But the good news is, in the setting of LQR, we are in a special case where we can compute this cost to go and also the feedback strategy quite efficiently, and we can represent them in closed form. And this is what we will look into throughout this part of the lecture. And so let's look at the recursive setup of the LQR problem, so sort of the dynamic programming perspective of this problem. Just as a reminder, here we have our original problem for LQR with costs, and so quadratic costs and linear dynamics. And if we look at the smallest possible tail problem, that is the sort of the smallest subproblem that we can solve, we can just look at the final stage. So we just look at the very last time step, and we can ask ourselves, okay, what is the best control that we can apply at the final time? And so we get only a single decision variable, because this best control that we're looking for is a function of state. So the state is given. And so from the perspective of this optimization problem, this is a constant because x is a constant. And then we have to just minimize this. And so because we assumed R to be positive definite, meaning that any non-zero control input would result in a positive cost, the best thing that we can do is just to simply not apply any input at all. And so the solution of this optimization problem would be that we don't apply any input. And in fact, it is also quite common to just get rid of these inputs at the final time entirely, because they will always just turn out to be zero anyway. And for the optimal cost to go, so at the final time step, we can just evaluate our original cost here, or the original cost to go, so which is just the last term of this summed cost, so just the last time step. So if small t equals capital T, we can just plug in the solution where u is 0. And so if we look at this, then if u is 0, then this term is gone, and all we have is this. And so the optimal cost to go as a function of state is just x transpose p x, where p is equal to q, where q is our state cost matrix. And so we will use this p to track the cost to go on the state, and which is something that we have to compute, and in contrast to this small q, which is something that we are given as part of the problem description. And so we have to, here finding p is trivial, we can just sort of look at this and see that p is equal to q, but later we will have to update it for the next time steps. And so let's look at how this update works. So now we take this, extend this problem one step backwards in time. So now we try to find the best input at the previous time step. So at the t minus 1, so the second to last time step. And so now we need to optimize over these two decision variables. So what we have to optimize is the immediate cost that we incur for the decision that we make now, plus the optimal cost to go, which is the cost that we incur for whatever state we end up in. And so this state that we end up in is connected to our initial state via the dynamics. And so that's why we have these dynamics constraints. And we can, for our particular problem, we can sort of plug in the things that we've already computed. So the immediate cost here, this G, is exactly our stage cost as we have defined it for LQR. So this is just this quadratic expression in states and controls. And then we can also get rid of the dynamics constraints. So here we still have the dynamics constraints and the decision variable for x. But here we can get rid of these dynamics constraints by applying exactly the same trick of forward simulation. So we simply replace xt, so which is the t at x at the final time step, so the next state. We can replace it with the dynamics, so that we now have only a decision variable as only the decision variable of the controls at t minus 1, and we have no constraints at all. And if we now substitute back our, so we already computed a closed form expression for the cost to go at the next time step, and so here we can plug this in. So we can replace this function with this expression x transpose px, and therefore we can write our optimization problem like this. And if we look at this, so we've just rearranged the terms so that here we have a squared term in x, then we have a squared term in u, and then we have a mixed term. We can look at this, so from the perspective of optimizing over u as a function where the solution is a function of x, x again is a constant, and so this is just a constant. This is a linear term down here, and the highest term that shows up here is a quadratic in u. And we can convince ourselves that because r was assumed to be positive definite and q was assumed to be positive semi-definite, and pt is exactly q, then positive semi-definite plus positive definite still remains positive definite. So this matrix this expression is convex quadratic in u, meaning that again we have this nice upwards curved cost landscape. And therefore we can apply the same trick as we've seen earlier, just now solving for only a single time step. And so we can find the global minimum of this cost landscape simply by setting the gradient to 0. So we take the gradient of the expression that you saw on the previous slide and set it equal to 0. Now we have to solve for u star to get the optimal input at the previous time step. And this will turn out to be this linear feedback strategy in the state. So we just have some matrix F multiplied with the state, which will give us the control which is the best control that we can apply at that state to fulfill our task. And this F matrix, so the feedback matrix, is computed with this formula, which is simply done by rearranging or by isolating u star here on the left. And whenever you see this inverse, you have to ask yourself, okay, can I safely invert this matrix? And we've just convinced ourselves on the previous slide that this matrix is positive definite, so we can safely do so. And then we can, this resulting feedback controller, we can now evaluate at an arbitrary state simply by multiplying that state with this matrix. Okay, that was the backup, so how we sort of compute the controls at one time step backward in time. Now we also have to back up the costs, so the optimal cost to go. We can again do that by plugging in the optimal control function into our cost to go. And so we will end up again with this kind of expression where we get a cost that is quadratic in the state. Now, so we again have x transpose px, but now this p at the previous time step is updated because we plug in this expression here for u in our cost function. And so again, we get this updated optimal cost to go. So the only thing that we now have to convince ourselves is what's happening with this matrix. So what are these properties? And you can show that this matrix is still positive semi-definite, even though we now took it one step backwards in time. And this is again derived from the assumptions that R were positive definite and Q was positive semi-definite. So therefore P is also positive semi-definite. And so all of this, composing this idea together, we already have the dynamic programming algorithm for LQR. We've now just seen how we can sort of back up the cost and the controls for one time step, but we can now apply this idea recursively. So we start at the initial time where we have seen that the initial cost to go matrix PT must be exactly Q. And then we can recursively compute the state feedback strategies for each of the time steps before that until we are at the initial time by applying this recursive rule, which is exactly the two equations that we have derived on the previous slides. So we can always back up sort of all these expressions from the next time step. So this is just the optimal cost to go matrix at the next time. So we know all of these because they are in the future, and we recursively going backwards. So we can, this way we can compute the feedback gain, and we can do the same for the quadratic cost. And with that, we then have a state feedback controller for each of the time steps. And we know that when we follow this optimal controller, we can ensure this cost, which is the best cost we can achieve in this given problem. And so to summarize, the main idea of the dynamic programming approach to LQR is that we can decompose the LQR problem into smaller one-step optimizations. So instead of solving one big batch problem over T, over all of the T time steps, we just solve T very small one-step problems. And the nice thing is that we can do this in a nice recursive fashion to get a state feedback strategy, and we can solve for these state feedback strategies one stage at a time. Now, a few comments on this approach, in particular in contrast to the batch approach that we've seen in the previous chapter. And so the main thing here is that instead of having to invert one big H matrix, which is MT times MT, so it grows with a horizon of the problem, we now only have to invert T, so the number of time steps that we have in the planning horizon, smaller matrices, which are always of the dimension M times M. So this matrix that we have to invert, which is perhaps the most expensive part of this whole computation, now has a constant size. It doesn't depend on the planning horizon. So this is now linear complexity in the horizon because we just have to solve more of these small matrices for a longer horizon, but the matrix itself doesn't grow. And the other nice thing about this approach is that we don't just get a sequence of controls that we have to apply, so just the values of the controls in open loop that are only valid for a very specific initial condition. Instead, we have solved for a feedback strategy that we can evaluate at arbitrary states. And this is quite interesting because it also allows you to compensate for errors. So imagine that you end up at a slightly different state. You don't have to recompute this whole optimization procedure again. You can just evaluate your feedback strategy at this new state estimate. Okay, so that concludes the section on LQR. So this bit of a deep dive for this special case where we could compute the optimal solution quite efficiently. Now we look at how we can use this idea to also solve nonlinear problems. So problems where we don't have linear dynamics, but potentially nonlinear dynamics, and also non-quadratic costs. And the main idea that we will exploit is that we can approximate the solution to a nonlinear optimal control problem via iterative sort of local approximations of the original problem as LQR, and then we can take small steps in LQR direction. And we will go into how that works here. So remember, for LQR, we could sort of analytically compute the global minimum of the cost landscape, and the batch approach and the dynamic programming approach were just vehicles to doing that in different ways. And so it's a bit simpler to think about this perhaps in 1D. And but if we now have a nonlinear cost, so our non-quadratic cost landscape, then we cannot solve this analytically anymore. But what we can do is we can exploit this LQR solution to take steps towards the solution, or steps towards at least a global local solution. And so what LQR or iterative LQR does is that we form a quadratic approximation of this cost landscape. So we do a Taylor series approximation here and Taylor approximation here. And for that, this will give us an LQR problem, which we can solve analytically to global optimality. And so this will take us in the direction of a local minimum. And so we sort of approximated the original problem about this red point, which is our operating point down here. And then we always step to this next point. And so now our operating point is this new red point down here. We again form a quadratic approximation of the cost landscape. So we again locally approximate this problem as LQR. And then again, we step to the minimum of the LQR problem. And if we repeat that sufficiently many times, then we will be at a local minimum, which is why we're using this different color for this. So here, there's another minimum over here, which is perhaps the global minimum of the cost landscape, but at least we can still find a locally optimal solution. And so if you've seen other approaches like the Newton's method, this will seem very familiar to you. And in fact, this is just a special case of the Newton's method where we exploit the very structure of this control problem. And so let's look at the algorithm of iterative LQR, for which you can see the flowchart over here, and we'll go through the idea of iterative LQR step by step. So the first thing that we need always for these iterative approaches is some initial guess. So we need to know some idea of controls that we may want to apply. And this can just be maybe for this car just slowly driving forward, can be a simple initialization. And the first thing that we will do is we roll out these controls to get the corresponding trajectory. So we can just take these controls, and we have the initial conditions from our state estimation pipeline. And we just apply the forward simulation function that we've defined earlier to get the entire sequence of states. So we know the initial state, we know all the controls, which we get from our initial guess. So these are not the optimal controls, but they're just some controls that we may apply, and then we get this trajectory. So these are the sort of step 1 and 2. And the next thing that we will do is that we compute, we want to approximate this problem as a LQR problem. So, and that is we need linear dynamics and quadratic costs. And so the first thing is that we do is that we linearize the dynamics about the operating point. So we've just, we have some initial guess of what the controls are, and we've simulated these forward in time to get the corresponding states. And now we can, if this was the original dynamics, potentially nonlinear, so here these blue dynamics, we can locally approximate these dynamics with a Taylor series expansion to first order. And so this is the operating point, which is the simulated state that we are at that time, and at this iteration of the algorithm. And so the affine approximation of this just goes through this point over here, this red point. So there it will be perfectly match the original dynamics, and then the further you go away from it, it may potentially deviate from the nonlinear dynamics. And so the Taylor series approximation about that point is exactly this expression here, where we've shifted our coordinate system into this point so that we are now not using x as a state, but we're using delta x, which we define as the deviation from the operating point. So we're asking ourselves, what are the dynamics around this point, our current operating point? And we do the same sort of centering about the operating point for the u. So delta u is just u minus u bar, which is the input at the operating point. And we exactly get, when we do that, we exactly get these linear dynamics that we've already know how to work with. So just a times x plus b times u, with a slightly redefinition of the state here. And these A and B matrices, they are simply computed from the Taylor series expansion. So A, for example, is the Jacobian of the dynamics in X. So how does this state change when I slightly apply a different, when I'm slightly at a different state? And same for B. This is the Jacobian of the original dynamics in U. And so this gives us these linear dynamics. We can apply the same trick for the cost. So if this was the original potentially non-quadratic cost, so this blue thing here, the blue cost landscape, then we can form a quadratic approximation this time about the operating point. So here, this was our operating point. Now we fit a quadratic function to that point where we want to match the value at this point. We match the slope, and then we also match the curvature. And so this is the quadratic approximation of g around this operating point, which again we write in terms of our delta state, so delta x and delta u, the deviation from this center. And if we look at this, this is exactly this part we already know. So this is exactly the quadratic cost that we've already seen. And that we know how to work with, and then there are some of these additional terms. And just for reference, these terms that show up in the cost, they're computed like this. We're not going over these in detail. These are exactly the sort of the same idea of Taylor series expansion that we've seen at the previous slide. But now we're asking ourselves, how can we work with the additional terms? So here we already know these quadratic terms. We know how to incorporate in the LQR problem. Now here are some additional terms that we haven't seen before. There's one further trick. When we want to solve the LQR problem, we can augment our state to now include an additional 1 at the bottom. And so we define a new state z as just delta x and a 1 as a 1 additional state component. We can do the same for the input. So instead of u, we now use v, which is delta u and then a 1 at the bottom. And if we do that, we also have to define the corresponding state matrices, and you can the corresponding dynamics, and you can convince yourself that this encodes exactly the same dynamics as before. So we just embed this a tilde here as the top left entry in this block diagonal matrix, and b we pad with a 0 on the bottom, or with zeros at the bottom. And then we can rewrite this quadratic cost q, where previously we had these additional affine terms. We can now embed these in the quadratic cost matrix here, and same for the control cost. And so you can convince yourself that also this cost, which is now here, represents exactly the same objective that we've seen on the previous slide. And so now we have this standard LQR problem that we've already seen how to solve, either with a batch approach or more efficiently with a dynamic programming approach. And we can just solve the solution, or find the solution of this problem. So now we are at this part of the algorithm. And then as the final part of our iteration, we will step towards this solution. That is, we've now found this global optimum of the local approximation about our operating point, and we want to now take a step in that direction. And that is, we will take our original operating point, sorry, this is this one, and we just take some step size alpha between 0 and 1 in this direction. So if we were to go a full size of step size 1 in this direction of delta u star, then we would exactly end up at this blue point, which seems like a good idea in this setting. But in practice, we may also choose to take smaller steps here. And we will see some of the trade-offs soon. Okay, and so now we are at the end of this iteration. Now we have to repeat. And so we have an updated operating point. So we have updated controls. We will roll out these controls again to get the updated states. Then we get a new approximation of this problem as a local LQR problem. And then we can solve that problem again. And we will repeat that until our operating point has converged. That is, until the state between iterations does not change anymore. Okay, so that concludes the algorithm that you can, the LQR algorithm that you can use to approximate nonlinear optimal control problems. There are a few or two practical considerations that I want to highlight here, which are important to make this algorithm work reliably in practice. And so here we'll just go over the main ideas of why that is important and what you can do to address these points. And so the first point is that we have to make sure that our cost landscape remains positive definite, or that our LQR problem remains positive definite. That is, in our original example here that we used to visualize this idea, we just formed this quadratic approximation and it was nice and upwards curved. And when we stepped to that minimum, we would actually make progress to a local minimum of the original cost. However, in other settings, when we linearize maybe about this operating point here, then the cost landscape may have no curvature at all, and that corresponds to this matrix that we had in our LQR problem not being invertible. And so, because this doesn't have any curvature, so it will have 0 eigenvalues. Or even worse, if we are close to a maximum, then the quadratic approximation of the original cost landscape will take this shape, and setting the gradient to 0 will not find a minimum, but a maximum. And so then this matrix is invertible, but it's just this update is pointing in the wrong direction. And in order to fix this issue, we have to apply what is called a regularization. And there are different ways in which we can regularize the problem. In general, our task is to make sure that this matrix here is always positive definite. So previously we've just assumed that this is positive definite, but we cannot now, because we just assumed that R is positive definite and P is positive semi-definite. But now these matrices are not, we can't choose these matrices, but they are derived from the local approximation of the problem. And so we have to make sure that when we take the Taylor series expansion, that these assumptions still hold. And a simple thing that we can do is to make sure that this expression remains positive definite. We can just add a scaled identity. So we add this identity matrix scaled with a small value rho, and we have to change this, or we have to choose this value rho sufficiently high so that this this local approximation is upwards curved. So this essentially just bends the approximation at this point upwards. And it will make sure that all of these eigenvalues are positive and we can invert, and we'll also take a step in the correct direction now, because now when you take a step we would end up here and we actually go towards the minimum. The second practical consideration that I want to highlight is a suitable choice of the step size alpha. So when we choose this step size alpha, we have to solve this trade-off between making a lot of progress towards the goal. So for example, here in our original operating point, if this is our local minimum, our global minimum of the approximation, a step size of 1 would correspond to exactly going to this star here. So we're making a lot of progress, and that is a good idea. But on the other hand, we also have to make, so for this example, it's a good idea. But on the other hand, we also have to make sure that we computed this local approximation with a Taylor series expansion. And this expansion is only valid for a local neighborhood of our operating point. So we have to make sure that we don't move too far because the local model is not very accurate. And here's an example of when that can happen. So imagine that we have this different cost landscape and we linearize about this operating point here. And due to some stronger nonlinearity in the original cost, this sort of curves upwards quite quickly, whereas our local approximation about this operating point predicts that the minimum will be here. And so if we were to take a full step size of alpha equals 1 to this minimum, we would actually not even reduce the cost, but instead increase the cost throughout this iteration. And so this harms the convergence of the algorithm, and we may not even be able to find this local minimum. And the fix to make sure that we take a suitable step size, so the fix to take a suitable step size towards the local minimum is this idea of line search, where we try to adaptively find a good value of alpha, essentially by trying out different step sizes. So for example, we try out step size 1, and then we see that the cost even increases. And so then we would, in a backtracking line search, we would just reduce the step size. So we now divide it by 2, and now we get the smaller step. So we have the original, we don't have to compute the approximation again, so we can still keep the same LQR problem. We just have to reevaluate the cost. And so now we see if we take a smaller step, then we are a bit closer. But we would still not accept this. We would still not accept this step because this blue point doesn't sufficiently decrease the cost. So it's almost the same height as alpha, and so we only accept steps that significantly reduce the cost. And so we would divide the step size one more time. And now we made only a small step, but we are very close to the local minimum here. And now we would accept this step because it's neither going up in cost, and it ensures a sufficient decrease. Okay, so that concludes this section on iterative LQR, which was the last section of this lecture. And so to summarize, the approach that ILQR takes is that we can, if we have some initial guess for the control, so we have some initial strategy that we can apply, then we can iteratively refine the strategy by locally approximating our original nonlinear optimal control problem about the corresponding operating point as an LQR problem. Then we solve that LQR problem, take a step towards the solution, and then repeat that until convergence. A few comments on this algorithm. So in general, that is a very efficient and well-established algorithm for nonlinear optimal control, in particular in robotics. And it works particularly well if the problem is sufficiently smooth. So if there's high nonlinearities, maybe even contact, then this doesn't work so well because the Taylor series expansion is not very accurate. But for many problems, for example, like the self-driving car, this is an excellent algorithm. And we've already seen that these additional tricks like regularization and line search are very important to make it reliable in practice. So if you have some robot that has to follow some track, you cannot just sometimes accidentally increase the cost, and so getting these practical considerations right is important for reliability. And finally, I want to highlight that this algorithm can also be extended to include inequality constraints. So here, for the scope of this lecture, we have simplified the setting by assuming that we have no constraints on states and inputs beyond the dynamics. But there exist extensions like penalty methods where we can include an additional cost term to represent these constraints, and we can adaptively estimate the weight for these cost term. Okay, so that concludes today's lecture. To summarize what we've looked at today, we've begun with a quick review of model predictive control, which motivated this deep dive into optimal control today, so the numerical methods for model predictive control. And we've started our discussion with a review of how you can eliminate some of the decision variables and the dynamics constraints to obtain an unconstrained optimization problem via forward simulation, and to hopefully convince you that you may have already seen this unconstrained optimization problem in other contexts. Then we've done a bit of a deep dive into how we can solve a special class of these optimization problems or optimal control problems, which are problems with linear dynamics and quadratic costs. And so we've looked at the batch solution to LQR, which uses the idea of forward simulation to solve this as one big linearly squares problem. And we've also discussed the idea of dynamic programming, which exploits the fact that we can recursively compute the solution to an LQR problem quite efficiently. And finally, we've pieced all of these different ideas together to come to discuss the iterative LQR algorithm, which is an algorithm that solves nonlinear optimal control problems through iteratively approximating the nonlinear problem as small or local LQR problems that we can use to find a step direction and make progress towards a local minimum. Okay, so that concludes today's lecture. If you are interested in reading more about these topics, there are several resources that I can recommend. So the first one is this book on predictive control for linear and hybrid systems by Francesco Ruelli, where also the lecture material for this MPC class from Berkeley is available online. If you're interested in more of the numerical background, in particular some of the tricks, how you can, the practical considerations, how you can make, how you can even get convergence guarantees and make these algorithms reliably work in practice, I recommend this book by Notodal and Wright on numerical optimization. And finally, if you are also interested in optimal control in general, trajectory optimization, and maybe some coding exercises, there's a course by Russ Tedrick from MIT on under-actuated robotics. Thank you for your attention.